All right, so as we wrap up this conversation of looking into this early world of congruence classes and then move into the awesome world of number theory and crypto systems, I just wanted to really quickly chat about probably one of the least secure ciphers in the entire world, the so-called Affine cipher. So even though the Affine cipher is complete rubbish when it comes to questions of security and actual application, it is going to serve as a very nice early application where we can start to see some of these pieces of terminology as well as some notation that we can then later apply to more interesting or elaborate crypto systems. The idea is that in this world, I'm still going to have some function that's going to encrypt something or encode something, and there's still going to be some function that's going to decode it. So I'm going to have an encoding function as well as a decoding function. Those pieces of terminology are going to exist in all of these crypto systems, so seeing it here is going to at least give you some early motivation that you're going to start to see something a little bit cooler as we build up some of the mathematics behind it. So in this case, what I'm going to be doing is I'm going to be looking at what's referred to as an affine cipher. So the essential idea here is that I'm going to take some phrase or some string or some sentence or just some collection of things that I want to take. I'm going to convert this thing to some numbers. I'm going to scramble these things up, convert them back to letters, and then send that message out into the universe. The idea is that somebody is going to receive this garbled message, and ideally they're going to have the ability, that secret decoder or whatever they're going to be working with, and they're going to be able to convert that thing back to the original message that I'm trying to send. For example, if I wanted to send this super secret message of MATH, which conveniently spells the word math, what I can do is I can actually take this word and I can actually convert it in the dumbest way possible. The idea is that I can take those four letters, MATH, and simply connect them to where those letters actually happen to fall in the alphabet. The idea is that the alphabet happens to have 26 letters in it. So what I can do is I can take A and I can send it to that first entry in this big set Z26. So Z26 is going to be this collection of congruence classes, which are going to be numbers like 0 and then 1, all the way up to the number 25. So what's going to happen is that letter A, which is the first letter in the alphabet, is going to go to the first entry in this thing, which happens to be a 0. So there's a little bit of awkwardness that's going to come into play, is that I would really want to think about A as being a 1, but the math is way easier if I actually send this thing to a 0. So for those of you in the computer science world, this is nothing new. The idea is that very often you're going to have these lists that are going to start at 0, and that's exactly what I'm doing here. Is I'm taking this big collection of letters and I'm just viewing that thing as a list, and that's going to be the entry that thing happens to live in. The idea is that A is going to live in that very first little cell, which is going to be indexed by a 0. Likewise, the letter M, which happens to be the 13th letter in the English alphabet, is then going to be connected to the number 12. So it's always that one back idea. So what you can see on this next slide is actually going to be this big laundry list of all of those letters on the right-hand side, then connected with all of their corresponding numbers on the left-hand side. So the idea is that the letter K is then going to connect to the number 10. Okay, so what else is going to be going on in this case? Well, before I move on too far, the idea is that I'm using these numbers 0 through 25 is actually just a bit of convenience, is that I do want to think about starting this process at 0. It would actually make maybe a little bit more sense to actually use where these letters are going to be living in that full-fledged ASCII alphabet, but I don't want to be dealing with numbers up in the 60s. The idea is that A is something like a 65 or 64, or wherever it happens to start in the ASCII list. It's much easier to view this as 0 through 25. Though if you wanted to deal this whole process with all of those special characters and all of the uppercase and lowercase letters, you could do something on Z26. You're just going to be doing everything mod 20, or you're going to be doing everything modulo 126. So for now, we're just going to keep this relatively small. So I'm going to be dealing with just uppercase letters, nothing else going on in this case, just very nice uppercase letters. Okay, so what I'm going to do is I'm going to take those four letters, MATH, and I'm going to connect them now into that string of four numbers. I'm going to have 12, 0, 19, and 7. If I were to take that little list of four numbers and send that out into the entire universe, everybody would be able to decrypt what my actual message is supposed to be. The idea is that they would say, hey, 0 is I bet supposed to be an A, 12 is supposed to be an M, 19 is supposed to be a T, and 7 is supposed to be an H, so I know exactly what your message is. So it's complete garbage to not do anything. And that's essentially what this is. Yes, I've officially taken these letters and written them as numbers, but in terms of actually encoding something, it's a pretty stupid way to encode things. It's really not doing anything other than making the transition from letter to number. But what's nice about this is that once I have numbers, I can start to use these things in very classic mathematical functions. So that's the first thing that we do need to know how to do, is take letters, convert them to numbers, because now that I have numbers, I can start to shuffle the deck using functions. Because that's all functions really do, is that functions are going to take a list of numbers and they're going to eat those things as inputs, and then they're going to kick things out as outputs. That's exactly what a function does, is it eats something and then it spit something back out afterwards. Some functions are more interesting than others, which are going to make other types of crypto systems, but at least a starting place is going to be, what happens if my function is just a line? And that's exactly what an affine cipher is going to do. It's going to take this string of 4 numbers and they're going to funnel them through some linear function. In this case, that linear function is going to have to be viewed inside of Z26. So it's going to be a modulus operator that's going to have to happen afterwards. So what's going to happen is that I'm going to take those numbers, 12, 0, 19, and 7. They're going to be multiplied by something, for example, a 3. And then I'm going to take that number and I'm going to add 10 to it. And then I'm going to reduce that thing mod 26. That reduction of mod 26 is just going to ensure that I'm going to be back in that little list from 0 to 25. So some pieces of terminology or things you may have heard before. One thing that people often see early on in their lives is something that's referred to as a Caesar shift, which is exactly kind of a special case of an affine cipher. The idea is that if I looked at something that was just an x plus 10, all that's going to be doing is it's going to be taking all of those numbers and they're going to be shifting them 10 units up. So the idea is that that A would then shift up 10 units. So the idea is that that 0 would go to a 10, and in this case we'd see a 10 happens to be a K. So all that would be is a Caesar shift, is if I didn't actually have a quote-unquote slope coming into play. But in this case, what I can do is I can then multiply it by a 3, so I get a little bit more scrambling action happening. So the idea is that you can build up more interesting functions here to get all kinds of crazy scrambling actions. The idea is that as long as I have some key properties, this process is always going to work. So formally what's happening is that I'm going to have some function, which is identified here, which is going to eat entries from Z26, which is just simply saying, give me a number from 0 to 25. It's going to do some stuff, and then it's going to give me another number from 0 to 25. And that's going to be my encoding function. I'm going to call it f, though sometimes people refer to this thing as an e. So I have an encoding function and then a decoding function, but I'm simply just going to call this thing f for right now. Later on we'll use e's and d's and things like that, but just to kind of keep us in that proper world of this properly is a function, I'll use f for function, which is something you've probably seen before. So what I have here is I actually have a couple different ways I can actually denote this thing. Over on the left-hand side, I have this idea that's going to make use of this congruence class notation. The idea is that I'm going to take 3x plus 10, and then I'm going to reduce that thing mod 26. I'm using that somewhat clunky bracket notation. And on the right-hand side, I'm going to probably have the one that I'm going to rely upon a little bit more. The idea is that I have this modulus operator that we've been using for a little while, and what I'm going to do is I'm going to eat those entries and then just take whatever number I happen to kick out and then reduce that thing modulo 26. So that's the one that usually students like to gravitate towards. It's a little bit easier to work with, so I kind of tend to lean on that one a little bit. Okay, so let's go into see what's happening with this phrase of math. So the first move in this case was to identify this thing inside of Z26, which m is going to kick out a 12, the a is going to kick out a 0, the 19 is coming from the t, and then that h is going to be a 7. So those are my entries inside of my input now. They're in my, in a sense, domain world, so I'm living over here. Now I'm going to feed those things through my function f, and then I'm going to see what my new output's going to be. And this is really just going to be a bunch of computations of some modular arithmetic stuff. So the idea is that if I wanted to compute f of 12, what's going to happen is that I'm going to shove a 12 inside of that thing. So it's going to be a 3 times a 12 plus a 10, and then I'm going to reduce that thing mod 26. Well, if I look at 3 times 12, what that's going to kick out is a 36, and if I add 10 to it, what that's going to kick out is it's going to be a 46, and that's going to still be done modulo 26. And if I think about 46 mod 26, if I subtract a 26 from that thing, what's going to happen is that that's simply going to kick out a 20. So the idea is that that letter m is going to become a 12, and now 12 turns into 20. And if I go back and I can actually see what 20 is going to be as a letter. So that's going to be a new letter U. Likewise, I can look at 0. So if I shove 0 into this function, this one's pretty easy to do. So 3 times 0 plus 10. This again done mod 26. Well, 3 times 0 is 0. Adding 10 is a 10. 10 mod 26 is just going to be a 10. And that 10 is going to connect to a k. If I look at the 19, so if I do f of 19, that's going to be 3 times 19 plus 10. Again, modulo 26. And if you do that computation, this is going to kick out something like a 67. And 67 mod 26 should actually kick out a 15. And a 15 is going to be a p. And the last one is going to be f of 7, which is 3 times 7 plus 10. Again, mod 26. That's a 2 right there. A 2 and a 6. 3 times 7 is going to make a 21, which is then going to turn into a 31. And again, reducing that mod 26 is simply going to leave me as a 5. And a 5, if I look at that, is going to be an F. So the idea is that my original message is MATH. My new secret message that nobody in the world can ever decrypt, which is a complete lie, is going to be this message UKPF. So that's the idea, is that I'm going to take these little words, M, which is then going to connect to a 12, which then connects to a 20, which is then going to connect back to a U. So here's where that little function is actually going to be applied. So the idea is that at some point in time, we just simply deal with these functions as sending numbers around and forgetting all about that they actually connect to letters, because that's what we do in math, is saying, I really don't care, let's send numbers around and then, I don't know, let somebody else deal with that, the fact that these numbers actually correspond to letters. But early on, we'll make that a little bit more formal so you can see, hey, M's are actually going to be sent to U's, because that's usually how people end up sending things around. On this next little side, which you can see is actually a little bit of that computation. I did it in 2 different ways. I have the original message, which is going to be this MATH, and then as function output using this somewhat clunky bracket structure. So if you like that, by all means, go ahead and use it. And then down here, I have that computation that I just got done doing. What I'm going to do now, which is hopefully spin my computer and not have everything break, is actually open this up inside of Sage. So you can see a little bit of how we can use some computation to actually save us a little bit. So first off, it's going to be a little bit of code to actually show how we can take numbers and convert them back to letters. So if I use this character command, this CHR, well, unfortunately, if you do CHR of the input of 0, it does not kick out an A, which is somewhat annoying. What it does happen to do is that if you feed it a 65, so again, that's that ASCII code index in this case, 65 is where the A is going to be living. So what we've officially done is we've taken all those ASCII codes and we've shifted them back 65 units, because we don't want to deal with all of these other random kind of non-printable characters and all the other awkwardnesses that are going to live inside of ASCII. So in this case, that's exactly why there's that plus 65 existing. If you don't like looking at that, just pretend that this is a list of 26 things that starts right here, and there was no coding underneath that at all. All right. So what I've done down below is I've actually created my function f, which is simply that little linear function. That's what I'm talking about when I say affine ciphers, is just lines. I have 3 times the input plus a 10 actually coming into play. So what I can actually do is I can actually use some technology to actually save me a little bit of work. So the idea is that if I identify my word as a nice little list of these things, I'm going to create a new word, which is going to be called scrambled, which I'm going to add letters to as we go. So as I cycle through all of those 4 entries in this word, what I'm going to do is I'm going to connect my x to actually kicking out what that value is supposed to be from a numeric point of view. So I'm going to take that m. I'm going to kick out that m should then properly be that number 12. So I can identify it as where it lives in the ASCII index and then subtract 65. So that's what's happening there. So this is just taking the m and converting it into a 12. Then I'm going to take my function, evaluate it at 12, and then reduce it mod 26. So that's what's happening here. Officially, there's a little bit of awkwardness that happens here, is that this thing is not a very nice integer. For whatever reason, Sage does not view that as an integer. So what I'm going to do is I'm going to take that y and then make it for sure an integer. Even though it happens to print out as an integer, it does not treat it as one. So I'm going to convert it back to an integer, and then I'm going to convert that thing back to a character using that CHR command, and then append it to the end of this little list of scrambled. So if that's a lot more programming than you wanted to hear, what's happening is that I'm going to take this word MATH, convert it to numbers, scramble those numbers, and then convert them back to letters and put them into a list is really all that's happening. So if I run this command, you should see those letters U, K, P, and F, which is exactly what we saw last time.